Welcome to the course of material selection for mechanical design. We are in the week 2, module 2, and we have just started to explore different mechanical properties that will be relevant for a product designer. You imagine that as a product designer, you have the free choice to choose and get any of the wildest material available on the earth. Okay? And right now we will have the freedom. Later on that freedom we will take it out because of other considerations, for example, manufacturing condition or for example, cost conditions, etc. But right now we are looking at that what material property will be the best for our application, and that is what we are exploring in this week. Now, what I have already discussed in the last lecture, I have talked about those mechanical properties which determine the effect of applied forces on shape and size of material. In other words, I have first considered the stiffness or the deformation of the material, and towards that direction, if you remember, we have talked about the modulus of elasticity as Young's modulus, shear modulus, bulk modulus and Poisson's ratio as some of the very important factors. So, these are the material properties, and the corresponding also I talked about that material index that you may consider. So, that is what we have discussed. Secondly, I have also discussed from that same study, but considering not up to elastic deformation, but going up to plastic deformation, the strength properties. For example, the yield strength, the shear yield strength. Yield strength can be of two types. One is when you are trying to break it axially, and another is you are trying to break it through shear. Then the ultimate tensile strength, compressive strength, which is also known as the crossing strength, and the bearing strength, which is sigma b. So, these are the things that we have already discussed. What are the new things that we will pick up today? Well, let us look into the next important series of properties which are related to fracture, and this is very important in terms of systems where the crack initiation is possible, and also the application may be of such nature that the crack can propagate and can create catastrophic failure. Now, towards that direction, we will consider the properties like fracture toughness, critical energy release rate, impact toughness. In fact, impact toughness is the first one that we have already touched in the last class, and let us just continue with it for some time, and then I come back to fracture toughness and critical energy release rate, that is KIC and GIC. Now, if you remember, in the last class we have talked about a very important thing, that when there is an impact, the energy will be absorbed by the system with which these the impact is happening, and that can happen with in the form of plastic deformation. Now, it is also possible that a part of the energy will be given back to the system which is impacting because of the elastic deformation. So, there can be elastic deformation as well as plastic, but overwhelmingly such impact, when we talk about the plastic deformation, takes the major role in it. Now, if this is the case, is there any way we can actually quantify it? Of course, I talked about the Charpy test, I talked about the IJOT test. These are empirical tests, but there is something which can be done, which can be much more sort of rigorous in nature, and that is what we will talk about, that what kind of quantification we can do. Well, the first important quantification is really how much of energy is absorbed per unit volume, and that means you have to consider in the picture that starting from the strain level 0 to the epsilon f, okay, that is still the failure point, how much is the total energy that is getting absorbed into the system. So, we have to consider the area under the stress strain curve, okay, and that we have to do for the entire volume. So, we have to have epsilon here, and we have to have a volume integral of it. Okay. So, if we have this energy absorption, which is something similar, if we try to look at it graphically, that sigma epsilon for a typical ductile material, let us take. So, it behaves like this, and then the failure happens. Okay. Now, then suppose this is what is my epsilon f, where the failure is happening at this point. So, what this integration means is that entire area we have to consider, okay, which means the initial part, which is that half sigma y epsilon y, because you know that this is where is the yield strength. So, half sigma y epsilon y, and then so this is epsilon y, and then you have almost we are sort of approximating the rest of the area as sigma y times epsilon f minus epsilon y. Okay. So, various approximations are there. In fact, the better approximation will not be even writing it as sigma y, but for materials like steel, what we do is that, so we have sigma y at this point, and we have, let us say, sigma ultimate at this point. So, we can take sigma y plus sigma u over 2. That means, somewhere average you do it, and then you consider that area. So, if you consider it in a conservative way, sigma y times the epsilon f minus epsilon y, naturally this region for a metal is quite big. So, this area is smaller in comparison to that. That is why many times we simply approximate it as sigma y epsilon f. So, that is the way we can sort of approximate the energy that is absorbed, and these can be done very easily through a test which is called a drop tower test. And the drop tower test helps you to calculate this energy that is actually absorbed in the system, and once you know that the energy that is absorbed in the system, you can also find out that what is the specific energy absorption. That means, ut over rho will give you the specific energy absorption, and that is one very sort of a common SB index towards this direction. Now, if I look at a drop tower test, so somewhat it resembles like this. So, you can see that from the top there is a weight that is actually coming down and hitting the system. Okay, and then we have transducers, sensors to measure that how these stress strain diagram, in the stress strain diagram, that how the strain is happening corresponding to the load that you are applying. And you, if say a mass m is coming down, suppose a mass m is coming down. So, I just a drop of a mass m, let us say from a height h, this is happening. So, then you are actually supplying the input energy as mgh, and you are absorbing the energy on the system as ut. Okay. So, the ratio of it can actually talk about the efficiency. So, this becomes the efficiency. Through the drop tower test, you can find out efficiency in energy absorption. So, a material which has a high energy absorption will almost like dissipate the entire energy, the kinetic energy or the the total potential energy that is coming up. Okay. So, that it will completely dissipate. On the other hand, some material will have a elastic rebounding, so that it will not dissipate the entire energy. Now, I will show you that we can actually develop a structure which can absorb this impact energy in a very efficient manner, and this structure is actually inspired from fish scales. Okay, so this is a fish scale of a rare fish which is known as coelacanth, and also it is available in some of the mantis shrimps in ocean. So some of their clubs are made of this particular structure, which is very good in terms of impact energy absorption. I will just show you each one of them. Now, what we can do is that, getting inspired by the structure, we can create a structure which is known as a Bolligan structure. Okay? So, that is very good in terms of impact energy absorption. This is the Bolligan structure for TPU material, which is at 90-degree angle. Okay? So, this is the way it deforms. This is the softest one that is possible in this direction, and then I will show you another one. This is TPU 0 degree, where you can see the deformation, the local deformation much more clearly. This is a TPU 0 degree for high absorption of impact energy. And if I take a stiffer one, okay, this is a PLA 30 degree, and then it is very, very steep, you see. So, you will not be able to see such local deformation even taking place in the directly with your eyes. I mean, you may have to have a very sort of a magnification, high magnification to see it. So, this is much stronger of the same type of construction. Different types of Bolligan structures that has been designed at the SMS's laboratory in terms of impact energy absorption and application for cases where impact takes a predominant role. Okay, let us say we are thinking of developing supporting structure for say rail bridge, for example, where the columns are subjected to heavy impact load. Okay, or let us say we are thinking of the landing gear of an aircraft. So, these are the cases where the Bolligan structure is good in terms of absorbing the impact energy. Now, another related property that can also measure that sort of impact or shock absorption, not only that, and also different other applications also in terms of failure, sudden collapse or failure of a system, that is through this property which is called fracture toughness. Okay. So, all engineering materials contain defects, and that may be due to the manufacturing process. For example, casting can introduce porosity, inclusions can come up, and there are welding defects always. Then there can be machining marks on the system, corrosion pits, fatigue cracks, service induced damage or impact damage. So, all these things are very common for engineering materials, and if such a thing is present in a material, then we have to keep in mind that stress will not be uniform. Okay? So, instead there will be large stress concentrations in the crack tips, and that can cause the failure of a system drastically. Okay? So, such a thing was not known to people in the beginning. So, if you actually check the yield strength of a material which is well above the average stress that a system is subjected to, then you may find sometimes that you are actually safe. Okay? So, let us consider that you are considering a frame, okay, for which you are applying this tensile force, and you could figure out that this is F and this the cross sectional area is say A. So, you can figure out that the average stress is say F over A, and then if this is much less than sigma yield, we say that the structure is safe. We say that the structure is safe. So, we sort of devise a factor of safety and say it is safe. But you imagine that you have a small crack here. Then what will happen? That the stress distribution will be non-uniform at this crack tip. So, the stress distribution would highly increase towards the tip of the crack. Okay. This was something not known to people earlier, and in fact, the most important thing is that when people started to make the aircraft windows or the windows for the ships, in both the cases initially the windows were like rectangular type. Okay. But then today you won't find any such rectangular windows. Okay. So, the windows are invariably circular. Why? Because then some spectacular failures happened, collapses caused lot of lives, and people understood that if you cut this type of a system out of a metallic plate, then these sharp corners can actually create very high stress concentration, and from there the cracks can propagate and the failure can happen. That is why people started to use the curved, whenever there is a cutout, the cutouts are invariably curved, so that the stress concentration comes down. Okay. So, this is when we see it, it is not just for aesthetic reason, but for a very important structural reason, that you want to reduce the stress concentration. Now, let us look into that how we are going to then look into the stress concentration. Now, thanks to George Irwin, this is defined the stress intensity factor in terms of y sigma square root of pi a, which means there is a geometry factor, there is the applied stress, and also there is this crack length or crack size. So, all of them together create the stress intensity factor, okay, which is naturally its unit is MPa square root meter. This factor actually determines that whether there is a possibility of crack initiation and crack propagation there in the structure or not. How does it determine? Well, first of all, of course, you have to find out what is the K corresponding to your system, okay, and then you have to see that this what is the level of this K, whether it is equal to KIC or not, okay, where KIC is called the fracture toughness. So, a structure in today's definition is safe as long as K is less than KIC, and if K equals to KIC or K greater than KIC, then always the fracture is going to propagate and there will be failure in the system. Now, this KIC which is the measure of fracture toughness for us. So, that can be of three types. Okay. One is the opening or tensile mode. As you can see that here this is the crack direction and the force is perpendicular direction. Okay. So, that is that plane, okay, that is perpendicular, and that is the opening or the tensile mode. And there can be another case of fracture where it is in a sliding mode. Okay. So, the crack is here and then you are having basically two surfaces which are shearing against each other. That is mode 2 type of a failure. Mode 3 is a tearing failure. In this case, what you have is the crack is here and the forces are in a plane. Okay. So, if this is the crack containing plane, forces are in a plane which is perpendicular to the crack containing plane, and out of plane and then through that the tearing is happening. So, that is K3. So, you have not just KIC, but you have KIC or KIIC or KIIIC depending on the application. Okay. So, you have to see that what is the application in your case, and accordingly you have to measure the fracture toughness, though in general we always refer it as KIC. So, you have to keep these three modes of crack displacement and crack failure. Now, let us look into that from the fracture point of view. If I want to look into the materials, then what is the KIC scenario? Well, you can see that the KIC is the lowest possibly in glass. In fact, glass contains lot of micro cracks. One of the simple experiments that you can do is that you take a small glass plate, okay, and let us say you take a small glass plate, support it at 2 points, and then you apply a force here and measure that at what force it is breaking. Okay. Now, you would see that this force is actually quite low where it is breaking because of the presence of the micro cracks, which is not visible, but it is there in the glass. Now, if you dip this glass in sort of a corrosive acid, then some of these surface cracks are actually going to be corroded away, and then if you do the same test, you are going to see that these load carrying capacity will increase. Okay. Later on I will tell you that that is why in glass fibers which is used in composites, we apply something which is called sizing in order to improve its fracture toughness. So, glass per se has one of the lowest fracture toughness. Alumina is also ceramic. So, ceramics have very low fracture toughness, as you can see. Concrete is also quite low. In fact, if you consider the metals, so the cast iron has good fracture toughness, even better aluminum alloy, then the titanium alloy, and then the structural steel, and one of the best is the maraging steel. Interestingly, maraging steel is different from structural steel in a way that it does not contain carbon. Okay. So, it has iron and also a certain percentage of nickel, cobalt and molybdenum. So, what happens is that in the process of annealing, we actually precipitate these each one of these trace metals inside, and these precipitations hardens it. So, it's called a precipitation hardening. In fact, maraging has two important things in it. Okay. So, it is a marriage between martensite plus aging, and aging is actually precipitation hardening, and that happens with this nickel, cobalt and molybdenum, and through this process you get a metallic alloy which has a very high fracture toughness. Okay. We will see later on that these sources of cracks and how these precipitation hardening can actually stop, why this happens. But right now just want to tell you that maraging steel is very good in terms of fracture toughness. Rubber also has a very good fracture toughness, but since it cannot take a large load, so we generally would not consider it for this type of applications. Now, what is important here is that as I told you that if you do this glass plate experiment, you will see that the load at which it is going to fail for the identical geometry is never the same, and that is because there is a probability of this micro cracks distribution which is different from one sample to the other sample. So, these probabilistically follow something which is called Weibull distribution, named after a Swedish mathematician Weibull. And the beauty of Weibull distribution is that you can actually shift it, okay, by shifting a parameter k. Okay, you can shift it. So, this is the green one is the generally standard Weibull modulus. So, this is standard Weibull propagation. So, this is the standard Weibull propagation. However, you can make it biased in either the left side or in the right side by varying the parameter. So, if k is less than 1, it gets biased in the left side. If k is greater than 1, then it can come towards the right side. Okay. So, the green one, k equals to 3 is something which is the most possible one, but k greater than 3 is something in which the right side bias may happen into the system. Now, what is the significance of it? The significance is that in general most of the systems will have the maximum number, will have this type of a distribution, be it in terms of strength, let us say. So, for a material which is, let us say, like a ceramic material, you would see that a large number of samples will have their strength in this region. However, there are some samples which will have very low strength, or some samples which will have very high strength. Okay? Their numbers will be very low. Okay? Now, this kind of a distribution pattern will be more apparent for ceramic materials, but for the non-ceramic, let us say for metals etc., this variation or this hump will not be prominent at all. So, for metals it will be almost flat. Okay. So, the way we measure it is something which is called Weibull modulus, okay, and that is defined in terms of Pf, which is the probability of failure, and that equals to 1 minus e to the power minus sigma over sigma 0 to the power m. Okay. So, that is the way the Pf is defined. Okay. So, where m is the Weibull modulus. Pf is the probability of failure, which from experiment you should be able to figure out that how much percentage of samples are surviving under an applied stress sigma. Sigma 0 is the characteristic strength at which approximately 63% samples will fail, and once you have this probability diagram, you should be able to calculate what is the m value. If the m value is greater than 20, it indicates a very strong material with a very high reliability, and if m value is less than 10, that means it has a very unreliable strength. Okay. So, as a designer, you should be always cautious of that what is the m value of your material. If it is high, you are safe against fracture, and if it is low, then it can have a fracture failure. So, that is the significance of this Weibull modulus. Now, the material selection property corresponding to fracture toughness, it actually varies. Okay. So, when we will discuss different case studies, we will show you that sometimes it can be KIC over rho, sometimes it can be some kind of an index of KIC, k square root of KIC or KIC to the power n etc. But generally you can consider the specific fracture toughness as a good measure as KIC over rho, and through that lens you can start to look into the materials choice. Okay. So, now you see it is not just the fracture toughness that is a picture in the picture that is important, but also the density of the system. So, managing steel has a slightly higher density. Okay. So, there is a density penalty. Instead of that, its KIC is so high that this comes out to be number 1 in terms of fracture toughness related applications. Then there comes a high strength low alloy steels, which has about 15 to 23 KIC over rho, structural steel 10 to 19, titanium alloys 14 to 25. So, they can be also quite big actually, titanium alloys, and stainless steel 15 to 28. Aluminum alloy has low fracture toughness in comparison to all other things. So, that is 8.5 to 12.5, okay, and so that you have to take care of. Okay. So, both 7075 and 6061 has applications in vehicles, but then you have to keep in mind that it is not as high as, let us say, the titanium alloy. Okay. That is why some of the very failure prone systems are to be made of alloys like titanium alloy or a super alloy, things like that. In fact, invariably for all biological systems, Ti6L 4V as a prosthetic device, is invariably made of titanium alloy, because when you are inserting a prosthetics inside the body, you cannot take a chance that if it suddenly breaks due to fracture. So, that is why it is so important. And also because it is KIC over rho, so it is lightweight, at the same time it has high fracture toughness. Now, if you look at some more material in the list, so I have just kept managing steel for comparison. Magnesium alloy could be the next hit, and that is about 8 to 14. Cast iron quite low, you drop anything made of cast iron, it breaks quite easily. So, 2 to 3.5. CFRP is also good, 12 to 29. GFRP is reasonably okay, and alumina is quite low. So, this is just to give you an idea that if you look from the fractures point of view, what material property to look for and how you can choose a material suitable for your application. Now, another important factor that comes here is called the critical energy release rate. So, the fracture toughness is from the force point of view, whereas critical energy release rate is from the energy point of view. The advantage is that for fracture toughness, you have all these modes that comes into picture, mode 1, mode 2, mode 3. For the GICs, it is the energy, and that energy is that for every fracture you are opening up new surfaces. So, how much of energy is spent for this new surface opening, that actually defines the critical energy release rate GIC, and that is certainly more profound, and Griffith first proposed this, that when the crack will propagate, you will see that the reduction in elastic strain energy exceed the energy required to create two new crack surfaces. So, if the elastic strain energy gets reduced in the process and that is more than the work you have to do in order to open up, then definitely it will be energetically favorable, and then the cracks are going to propagate. And the way we are going to measure it is G as minus du dA, where U is the elastic strain energy and A is the crack surface area. G is generally measured in terms of joule per square meter. Now, this the critical energy release rate is related to fracture toughness. So, GIC is KIC square over E, which means that if you know KIC already and knowing modulus of elasticity, you should be able to calculate what is the strain energy release rate or GIC. I will show you some of the common values of GICs. So, for the glass, it is 5 to 15, and you look at it as some of the very high ones, structural steel, titanium alloys. You can understand that why making a crack is so difficult, because the energy requirement will be so high to let the crack propagate. Unless the system is subjected to very extraordinary large forcing condition, the cracks will not initiate, the cracks will not propagate. On the other hand, for glass, alumina, silicon, cracks will propagate very easily. So, that is what the GIC values are signifying. Now, CFRP is not that good actually. In fact, that is why sometimes one has to toughen the CFRP, so that it gives you a better GIC. Epoxy resin, which is often used in matrix in aircraft, they always contain cracks and they always degrade the property. So, that is why it has a large variation and it is quite low in comparison to the metallic systems. So, this actually gives us a fair idea about how to choose a material from the fracture point of view. So, this is where we end this lecture, and in the next lecture we will talk about fatigue and other properties. Thank you.